Hello, everyone. Welcome back to the AAS YouTube channel, and we are here with the good stuff, which is the AAS authors. And I am super excited to have Anna Bonaca with us today. Hi, Anna.
Hi, Frank. Nice to meet you. Pretty good. Yourself?
Doing well. Just got back from taking my daughter to the dentist, so that was exciting. All is good, but we needed some attention there. So where are you at?
I'm here in Cambridge, Mass, still working from home. I'm a postdoctoral fellow at the Center for Astrophysics in the Institute for Theory and Computation.
Oh, okay. Okay.
Yeah.
Very good. And that is a really unique background you have there. Is that like painted on the wall?
Yeah, it's actually like a
real bike
stand, so there are like a couple of them. Yeah. So yeah, like have to resort to all sorts of tricks when like in having a home office.
There you go. There you go. Very cool. What do you like to do for research?
I really enjoy studying our galaxy, the Milky Way. I think it's a great place to learn more about the I know, taken out of context. Yeah,
we like it.
It's awesome. It's the best. Some would say the best. But the reason I really like studying Milky Way more than other objects in this wide universe is that I think it provides like this great environment where there is a lot of sort of physics and astrophysics on display, but we still have many ways of studying all of those different processes that are going on in our galaxy. So I feel like there's still like a lot of data that like to test different theories, but it's sort of like big enough that like you can study questions of sort of cosmological importance in this environment.
Cool.
Yeah.
Very cool. In fact, we're going to be covering one of those papers today, so why don't we go ahead and get to it. So today we are going to be covering high-resolution spectroscopy of the GD1 stellar stream localizes the Perturber near the orbital plane of Sagittarius. And Anna, take us away.
Yeah, so really much in line of what I said I'd like to do. This paper gives us some interesting updates on the search for low mass clumps of dark matter in our galaxy. And this is really exciting line of research that only recently sort of flourished to its potential that people were hoping for it would happen thanks to the space mission Gaia from the European Space Agency. So what we're going to be doing here, anyway, for context maybe first, I was interested to see if there's any evidence for the existence of these low mass clumps of dark matter, because the cosmological model, lambda CDM, predicts that there should be, that dark matter is some sort of massive particle that can clump on these small scales of like a million solar masses and even lower, all the way sort of to Earth mass. And those clumps of dark matter wouldn't hold on to any gas, wouldn't produce stars. It would be just clumps of dark matter. And they're somewhat uniquely predicted in these sorts of models if the dark matter is cold. And there are other models of the universe, of cosmology, in which dark matter is not cold. It can be warm, so it could be fuzzy. So in those models, we don't expect these sorts of dark matter only clumps to exist. So in a way, searching for like their existence and being able to conclusively say whether they exist or not would tell us directly something about the nature of dark matter.
Yeah.
And that's of course important because now we are pretty certain that 90% of the mass in our galaxy is dark and like in the form of dark matter, and yet we don't really know what it is. So in this paper, what we try to do is see whether like this object in the title, the GD1 stellar stream, was impacted by such a clump of dark matter. And these objects, stellar stream, like the GD1 that I study, they're actually disrupted globular clusters. And so you can kind of imagine a globular cluster being pulled away by tidal forces by the Milky Way. So it starts like compact, kind of spherical, and then gets kind of sheared out into like a very thin ribbon of stars that are orbiting the Milky Way. And since it is sort of this exquisite, almost one-dimensional structure, we expect it to be very sensitive to any sort of gravitational perturbations that it could encounter in this Milky Way environment, such as, for example, the clumps of dark matter. So that's why I'm particularly excited about using these disrupted globular clusters as tracers of kind of this fine structure of the dark matter halo of our galaxy.
Maybe you'll get to it, but since we're talking about streams being pulled from globular clusters, do we have an idea of how old this stream is?
Yeah, so we think the dynamical age of this stream is something like 4 billion years, but the stars inside of it are like 12 billion years old. So it definitely seems like we are like either we are not seeing the whole extent of the stream, or it's just like took some time to start disrupting, or like to disrupt in full. So yeah,
so it was
but it is
about 8 billion years and then ran into the Milky Way and rip.
Yeah, so but definitely it had like time to wrap around the Milky Way, something like on the order of like 10 times or so, at least 10 times. So it has been kind of orbiting around for a while. And maybe like to kind of give a visual sense to our viewers, like if you go to figure 2, we can see sort of how like a precursor to this work over here. So in the top panel of figure 2, I'm showing likely members of this GD1 stellar stream in the small, like the black to small gray points. And this really like research was enabled by the Gaia mission that I already mentioned, and it's actually a funny story of how it came about. So
do tell.
Yeah, it's kind of like we've known. So this is a stream that was discovered in 2006 by Carl Grillmeyer and I don't know this first name of the second author, Dionatos, but anyway, so GD1 is like named after the discoverers, it's so we think it's a globular cluster stream. You can see like on the coordinates here, like phi1 and phi2, so angular coordinates oriented such as the stream lies on phi2 = 0, basically. And you can see that it is a very narrow stream. So this is why we think it's a disrupted globular cluster. But that also means that in a globular cluster, there are only so many stars. In the Milky Way, there are way many more stars. So it was actually hard to map the stream, and really impossible to plot individual stars as is done here. And that was only enabled by the Gaia mission. And so this selection dates from something like the third day after the data, like the second data release from the Gaia collaboration. And I was attending a sort of a launch party for this data set that was organized by the Flatiron Institute and their Center for Computational Astrophysics in New York. And I teamed up with another postdoc there, Adrian Price-Whelan. And we were like, okay, like, let's look at this object. We knew it was there. It was like discovered 10 years before. I wanted to check, like, what is the Gaia view of this structure? And the reason we thought it would be interesting to look at with Gaia is that instead of just selecting likely member stars just based on their colors, because like globular cluster, we expect them to be sort of bluer than a typical star in the Milky Way. And this is kind of how all of these streams so far were being discovered.
Mm-hmm.
But with Gaia data, we sort of knew that expected the stars to be all moving in the same direction if they're in the stream. And for this particular stream, it turns out that it is moving in a direction like opposite from most of the stars in the Milky Way. So it's retrograde stream. So it was like really easy to pick it out, which is why we managed like on the first day to get a map that was already like orders of magnitude better than anything we had before. And we were just struck by like immediately how much detail there was in this map. We like extended the stream like 20 degrees further than was previously known, just because we were like able to map this kind of low surface density part of the stream. But in this paper, what we focused on are these features around minus 40 degrees. So you can see that there is sort of an underdensity of stars there compared to the other parts of the stream. And also it looks like there's an offshoot of stars like between minus 38 and minus 30 degrees, sort of above the stream.
Yeah.
And that was really puzzling for us. So we kind of knew like this existed. We expected something like this underdensity could form in the stream and this was actually proposed as a sort of indicator of a stream having encountered dark matter subhalo or something else, which would then kind of create this underdensity or gap in the stream. What we didn't expect was like this offshoot of stars that appear to be moving in the same direction and have like the right colors, but were just like significantly offset from the rest of the stream. So this is sort of where this paper that we were talking about comes in, trying to understand what are those stars? Are they actually related to the rest of the stream? And if so, how? Like, how did they get to move outside of this bulk of the bulk stars in the stream?
Yep, I'm with you.
So, like the immediate thing we thought like would be very informative was to get the high resolution spectroscopy of stars, both in this spur, like outside of the stream, and in the mainstream.
Okay.
And sort of our goals were twofold. Like one was to get measure the chemical abundances of those stars. So because if we expect them to have similar abundances if they're part of the same structure. And if they would have very different abundances, then it would probably mean there is something unrelated and sort of chance projection in the sky that they appear like related in the Gaia data. And then another product of like spectroscopy, it turns out if it is that we also get radial velocities, which are or at least for these stars, haven't been released with the Gaia data a couple of years ago. And if it turns out like that based on chemistry, it appears that the spur of star is related, is a part of the whole stream from the relative radial velocity, we might learn something about their origin and how they got to be displaced from the rest of the stars.
Let me ask you a question.
Yeah.
You know, certainly in the last decade or so, we've seen multiple lines of evidence of globular clusters having different main sequences or different sequences within the globular cluster. Would that potentially have an impact here, or is the difference in, for example, FE over H small enough that you wouldn't pick that up here?
Yeah, you'll like see in a bit that we don't really have the precision to do that. Okay. But I think it actually is a very interesting point, and it's something that would be good to check in the future. I mentioned that we think this is a disrupted globular cluster just because of how thin it is on the sky. Like, I think the really kind of nail in the coffin piece of evidence would be if we could detect those multiple population and like anti-correlations.
That would be wild.
Yeah, that would be wild. Like, hasn't been done for like any stellar stream in the Milky Way. But I think like we now have, like with this paper, I think we have at least a motivation to propose such observations. Yeah, so it's a very good point. Yeah. But it is hard, and like the reason like these sorts of studies haven't been done is that if you kind of look closely in this figure, you can kind of count stars individually, like the likely members from Gaia. And then when you look at the axis here, you'll see that they are spread out like so sparsely over the sky. And these are fairly faint stars as well. So between, yeah, I think all those are fainter than 18th magnitude. So to get high resolution spectroscopy, like for a number of those stars, like you're really kind of hard pressed to find an instrument where you can do this sort of research. And feel like really fortunate that the University of Arizona and the Smithsonian Astrophysical Observatory are still supporting the hectoshell instrument on MMT, which is a high resolution multiplexing spectrograph that has 240 fibers and spread over a degree field of view. And it's on a 6.5 meter telescope, so that kind of hits all of those large apertures, so you can observe the faint stars, has the resolution, and still like you're able to get a decent number of targets in a single field. It's still an expensive project, but this really is the perfect, if not the only instrument to do it on.
Nice.
So yeah, what we then ended up doing is targeting 8 fields with hectoshell, and they're shown on the top in sort of bluish. You can see that those are the ones that are kind of on the mainstream, and in orange are the ones that are on the spur. And as I mentioned, we have 200 fibers available. We expect something like 5 to 10 member stars over there. So we like targeted a lot of other stars and want to just make sure that like we get everything that is plausibly a member. So we can go back now to like now that sort of we have our game plan here illustrated sort of on the first panel here. We can go to the first figure where we kind of walk through the process of identifying members from this sample where we of stars. So all of the stars that we targeted are shown in the lightest color and the small points. And then we sort of just developed a series of selections in these different properties, each illustrated in a single panel, to kind of narrow down what we think are most likely members of the stream. Okay. So starting sort of from the top left, this is the proper motion diagram. So you can see, and where we expect the stream stars to be is within this dashed box. So you can see that we did target like stars outside of it just because there are so many available fibers. Right. So as the first step, we just select stars like in this proper motion, and then we are left with 168 stars within this box, and they're shown as this larger medium light, medium blue points. Like our ultimate selection, like once we apply all of the selection criteria, are in dark blue. So you can see that it's like actually the box is fairly generous, is I think what this is saying. However, when we take all of the stars within this proper motion box and plot them in the color magnitude diagram, so this is the middle panel on the top, you can see that many of them are following this, falling in this weirdly shaped box, which is just selection around the isochrone for an old and middle core population. So once we applied that criterion too, which is what we got. So first we got proper motion information from Gaia, then this color magnitude information from Pan-STARRS photometry. Then we can plot just the distribution of radial velocities or relative radial velocities with respect to the expected orbit of the stream. But you can see that they are mainly on the top right panel. They're mainly concentrated around 0. And this peak is fairly narrow. So we further select members that are only within 7 kilometers per second from this orbital radial velocity at a given position along the stream.
Okay.
And then on the, we're keeping count. So this leaves us with 53 stars. And then on the bottom, I'm showing the chemical information for these stars. So we have the alpha over Fe abundance versus Fe over H abundance. And you can see that, there's distribution. Most of them are very metal poor. Looks like that some of those extremely metal poor stars might be outliers. So we just ejected those and selected stars around -1 of Fe over H and adopt these 43 as our main sample of member stars here.
Okay. And metal poor and alpha enhanced.
Yeah, interestingly, there is most of them are super solar, so alpha enhanced. However, there is a spread, although the error bars are large, and I think this goes to answer your earlier question. So with the spread both in alpha abundances and in iron itself is now consistent with just being with observational uncertainty. So we don't know if there's any intrinsic spread here or not. But I think it is exciting that both stars in the stream, in the mainstream, which are shown as circles, and in the spur, which are shown as stars, are kind of showing this whole this spread. So they do look like they have similar distributions and that they actually are part of the same structure. Mm-hmm. And I think this does motivate getting more precise abundances, different chemical elements to see if there are any in the those smoking gun signatures of globular cluster kind of abundance patterns. Mm-hmm. So that would be very exciting, just to understand this object and its history better, and also a little bit for understanding its disruption, its evolution in the Milky Way, because there is some kind of radial gradients, dependence on the existence of those populations in globular clusters. So mapping that out in a stream might tell us something more about where the progenitor used to be, which would be kind of a unique way to do it. And I should say this is a completely disrupted globular cluster. We don't know where the progenitor used to be, and that would be very helpful in further modeling, dynamical modeling of what happened to it.
Right.
Yeah, and that's sort of exciting now because now that we think it is a part of the same structure, we can kind of go check the radial velocities of those stars in the spur and in the mainstream and see what we can learn from that about why did they those spur stars move out from the stream. Right. Yeah.
Cool.
So if we go now back to figure 2.
Figure 2. Here's our radial velocities. Okay.
Yeah, so here, now so we are familiar with the top panel, which shows now again all of the Gaia detections of stars in the stream as small points. Then our members that we identified in this work in the mainstream as blue points and in the spur as orange stars. And in the larger gray points are literature measurements of radial velocities in the stream. And so on the middle panel shows the radial velocity of those stars along the stream. So you can see that our measurements agree really well with like the overall trend in radial velocity. And this is just driven by the orbit of the stream. Since it's like orbiting around, we don't expect the same radial velocity at every location in the stream, but instead there is like this fairly steep gradient in radial velocity.
Yep.
So we it was like really good, and yeah, completely expected that we do recover the same trend. Interestingly, like thanks to the higher resolution of the hectoshell spectrograph, we see much less scatter in our observations. And when we sort of subtract out this orbital trend of radial velocity along the stream, we see the kind of relative radial velocity on the bottom panel. And you see that there is really not much difference in radial velocity in the mainstream and in the spur. Right. This was sort of expected, like when we saw that histogram in the first figure, it was fairly narrow. There was a single peak, but like looking at this figure, so we had two fields that were observed at the same location in the spur and in the stream, so around -33 and around -30 degrees. And when we averaged the radial velocities in those fields, we see that the offset is smaller than 1 kilometer a second between those two, like these different parts, like in the spur and the stream. So that was, well, another evidence that this is likely a part of the same structure. It would be extremely unlikely that these are like just a random, uncorrelated like group of stars that has the exact same chemistry and exact same radial velocity as the stream. But it also turns out that this provides us some interesting clues as to what might have happened to displace these stars outside of the stream. And this is basically what then we explored in a little bit more detail in the next figure. So this is building. So this figure is building up on some previous work I did last year when I wondered if that structure of a gap and the spur of stars, if that can be produced by that mechanism. If an object hit the stellar stream, we kind of expected that it can form the gap, but I was wondering, can it also like pull some stars out of the stream? Right. And so I ran like a bunch of simple, like very idealized models. And yeah, it turned out that you can produce that kind of morphological feature on the sky. And it was like one of the parameters that we varied was the mass of the object, another was its size. So we were getting solutions in that cosmologically interesting regime of like where we would expect this empty dark matter subhalos are completely dark, but they were getting, or like the solutions we were getting were more compact than what we expect for clumps of dark matter in the lambda CDM cosmology. So there's more like a globular cluster, so kind of massive but fairly compact. And so like one idea was in like, well, that's great. We can then just go look where this thing should be and try to observe it. If it's like some faint globular cluster that we haven't, found previously. Like if we like just stare long enough, we are bound to see it. And so the top left panel here is showing our first attempt to do that. So this is taking all of those models from my 2019 work to sort of produce the right morphology of the GD1 spur, and then ask, where are those objects today? The answer is they can be literally anywhere on the sky,
Okay.
which makes it hard to follow up. But then in this paper, we kind of know we have an additional constraint. We know that they should, like this, if this is a scenario that displays stars out of the stream, it should not just like put them on the right kind of distance from the stream and kind of at the right length. It should also have this very little radial velocity offset. So if we include that as an additional constraint to just remove objects from this kind of sky view, we are left on with this top right panel. So this is again showing the distribution of all of those like models, scenarios in which an object encounters GD1, produces the spur at the right place, and moving at the right velocity that we observed here. And so now here, okay, it looks like, you know, it's not a very fine localization, but we did remove a lot of real estate here. And so that was already exciting that we kind of, this idea sort of might work, that we might actually predict, okay, if something happened, it should be like in the specific regions of the sky. But then when we looked into this in more detail, it looked like this is another kind of random patch of the sky. It looks like it's astrophysical. It looks like that's an orbit or something.
Right.
And so then we're like, okay, we know there is something that looks like this on the sky today.
Yes.
I'm showing this on the bottom left panel, the expected distribution of dark matter particles from the Sagittarius dwarf galaxy. So Sagittarius is a dwarf galaxy that is being tidally disrupted by the Milky Way. It produces like a huge stellar stream that is basically polluting like much of the halo. It's like a very unlike the one that we are studying here. It's like 10 or tens of degrees wide. So because of course it formed from a more massive object, it should have been also associated with its own dark matter. And so if we, of course, don't know where that dark matter is, so this is why we used a theoretical model from Miriam Dierix and Avi Loeb. And this kind of by eye looks like close enough. So if we just take this running median of the predicted Sagittarius stream on the bottom left, and over plotted on the bottom right on our solutions, it kind of looks like a tentative association that this yeah, it's exactly very suggestive. Right. And so we thought that this was like really exciting, just not just for this fact that we can perhaps localize it on the sky, but maybe that we can also provide some actual origin of this object to map it, at least suggest a mapping to Sagittarius. And we, like in the version that we first posted on the archive of the paper, sort of stopped here. But then our referee was like, okay, well, this is very interesting. Like, maybe you can explore this in a little bit more detail, because, and it's a very fair point that this is just a projection in the sky. And the referee asked, like, okay, do the actual 6D orbits of these GD1 perturbers, like objects that we hit the stream that produce the right morphology, do they agree with the kind of 6D orbital distribution of these Sagittarius particles? Yes. And this is basically what we explore in the final figure here. So the blue is showing, so the blue field is showing the sort of smoothed density maps of the Sagittarius debris from that same model in XY, XZ, and YZ projections. And the arrows are just showing the light blue arrows are showing just kind of the velocities of a subset of those particles.
Mm-hmm.
And orange arrows are showing the velocity vectors in those spaces of these GD1 perturbers on the progress side. And so you can see that, and like almost all of these projections, they trace this inner edge of the expected distribution of Sagittarius, and also that the kind of error velocity vectors are sort of aligned with those orbital kind of paths, which is exactly as we would expect for a physical orbit there. So that was, I think, like a really nice comment from the referee that made this association much like from suggestive to at least, you know, a little bit more plausible, and sort of definitely meriting something to take into account going forward. And
so the review process worked.
Yeah, it did. It was such a pleasure. It really was. Yeah. So, and I guess my experience with AAS publishing has always been very pleasant. So I can, definitely give a shout out there for all of the hard work that the editors and referees do. So I think this is all very exciting. There's still a lot to do. So given that we've mapped sort of the origin of the object to Sagittarius, is exciting, but we still don't know if it's, it could be a globular cluster still. It could be a dark matter subhalo, but now at least we know sort of where to go look to tell the difference. Yeah.
Cool. So I couldn't help but go back and go down into the references and find what GD is. So it's
Yep.
Carl Grimlar and Dion Atos?
Dionatos, yeah, but I don't know what O is.
Okay. Well, we'll
Yeah.
look up. There we go.
Yeah.
Very cool. Well, thank you for sharing this lovely APJ letter with us. And if you had to look in your crystal ball, where do you think the field is going with regard to perhaps this particular stream or to other streams over the next couple of years?
Yeah, I think there's definitely a lot more to do on this particular stream. This is just like this paper only had this spectroscopic follow-up on the like this small region of the stream, just something like 20 degrees spread. Like the whole stream is more than 100 degrees long, so there's just and there are other features there, so definitely not a complete story. I'm especially excited about how kinematically cold it seems. That was somewhat of a surprise. Yeah, and yeah, like all of those like stars, like the radial velocity measurement, they're like basically on the line. It was uncanny. Megan Jaluka, who is a junior at Northern Arizona University, will be analyzing this data as part of her RU project this summer to try to estimate whether like this coldness of the stream puts some constraints on how fuzzy the dark matter is.
Okay.
In different models of dark matter, you expect different amount of perturbation, like small from these small fluctuations in the dark matter field. Right. So it looks like that might be another handle that we can use this data for. Going forward, I think it's definitely exciting, like, to think of this stream as a pathfinder of what we can expect to see in other streams. It will not be as nice. This was like a lowest of the low-hanging fruits.
Yeah.
It is, you know, it's the closest, it's the most retrograde. It like peaks out really nicely. But these processes should be happening in other stellar streams, and I think it'll be really exciting to start analyzing them as a population to truly understand the global Milky Way environment and put some tight constraints on any of those small gravitational perturbations if they exist in the galaxy.
Cool. The future is bright. Seems like
it is.
All right. Well, I want to thank you, Anna, so much for your time this afternoon and sharing your lovely APJ letter with us. Thank you.
Thank you so much for having me.
All right.
Bye.
Bye, everyone. We'll see you on the next one.